Welcome to the APL Quest. See APL Wiki for details. Today's quest is the 8th from the 2014 round of the APL problem solving competition, where we are to compute the distance between 2 points in n space. This is really a very simple problem. The distance is the square root, that is the 2 raised to the power of a half, of the sum of the squares of the differences along each dimension. So we can test this. And we have another test case. This is 2D space, so let's try a 4D space as well. We can say U1, A, V1, and U2, A, V2. Right. So this really solves the problem, and there's not much variation one would really want to make here on this. However, there are some interesting things we can do since we like computing things on entire arrays. And let's try to do this on multiple arrays, on multiple vectors at a time, or points in the space at a time. And so there are some fun tricks that we can take care of here. Let's say we have a collection of points, but this U1 and U2, they don't have the same number of dimensions. So if we try to mix them into a flat matrix, then we end up getting padded with zeros on the right. That's actually not a problem because when we do the same thing on the other point, we get 0, 0 minus 0, 0, squared, sum it. It doesn't actually contribute anything, and so it doesn't hurt our computation. That means we can kind of upgrade all points to the dimensionality of the point that has the highest number of dimensions. So we can try this. And that works quite well. Now, here's the thing. We might want to define our function in terms of leading axis. Notice here we have summation along the trailing axis. And indeed, if we try to express this in a tacit form, then we naturally end up there. Because there's a common trick to use the problem of having multiple or even one monetic function inside a test definition. If we try to do this, then there's a problem here that we have a monetic function here. What we could move it over as a top on the power, but another trick is to use one base as summation, which might even be faster on non-integer numbers. And now the summation goes vertically, which means if we try to use the same thing, we get an entirely wrong result. That is, of course, because we are subtracting the two matrices correctly, and then squaring them correctly. And then we have now, in our case, a 2x4 matrix, and instead of summing along the rows, we are summing along the columns, and that has we're mixing up the two inputs that have nothing to do with each other. In that case, we would want to state our arguments in transposed form, which means that each row, or for that sake, each major cell represents one dimension in n space. So this can work as well. To spice things up a little bit, let's do some code golf as well. So we've got B here, but we can actually we can create something that's a bit shorter. We can remove the 0 from this power here. It decreases readability, but it does save a character. And then here we are summing the squares. Now summing a square is the same thing as summing the self-multiplication. And so we could write that as summing on the self-multiplication here. But this you should recognize as being an inner product. And so we still not this is still not correct syntax because this is a magnetic function applied on this static function here. And so we could make it at top, and that would have about the same performance as before. But because this is a selfie, meaning we are taking the difference and using it as both arguments on the inner product, then we could just subtract twice, which of course is a waste of computation resources, but it can be done. So we could state it like this. So this is a fork, and then that's used as the right sign in this for the fork. So this is code golfed away, and it will still work, but it won't work on the higher rank arrays because it's trying to do a matrix multiplication of two arrays that are two matrices that are not conforming with each other. So that doesn't work. Finally, note this, that we're doing a subtraction, then we are squaring, summing, and then the square root, which is the square root is the inverse of the square, which means if we had the under operator, which allows you to do some operation, so to say, under the influence of some other operation, we could sum under the influence of squaring. Now we don't have that as a primitive, but we do have it in Apple Cart. So we want the under operator that uses the inverse, and we get this formula over here. So let's call it like this. And now we can use can write a definition here which uses under. So it's very simple. It's just summation under squaring or self-multiplication, if you want, on the difference. And then we can try that. And we get the result. And it should even work with our high rank things because it's the same summation along the rows as what we had before. And if we had, if we compare now our code golfed thing here with using the under operator, this is kind of nice. Then there's it's one character longer. But if there was a primitive under operator, then it would actually be a character shorter, in which case I would say the nicest looking expression would also be the shortest one. Thank you for watching.